In this video, we are going to talk about the boiling point of organic molecules. So let's say we have propane and that we have pentane. Which one of these is going to have a higher boiling point? Well, pentane is going to have a higher boiling point, and the reason is because pentane has 5 carbons and 12 hydrogens. Meanwhile, propane has 3 carbons and 8 hydrogens. The more atoms that are in an organic compound, the molecular weight is going to be higher. And when molecular weight is higher, that increases the London dispersion forces, which as a result increases the boiling point. So let me explain London dispersion forces. When you have a nonpolar molecule, as we do here, the predominant force intermolecular attraction is going to be dispersion forces, and dispersion forces are greater in, for example here, pentane than propane, because pentane has more carbons and it can have more interactions as compared with propane. And so more of those interactions means that it is going to be more difficult to break up that force, and which means you need more energy to do it, and that energy comes in the form of temperature, so the boiling point is increased. So now let's go through our next example. Let's say we have propanol, and then we have hexanol. Which one of these is going to have the higher boiling point? So once again, it's going to be the larger molecule. It's going to be hexanol. They have the same hydroxyl group at the end for each of them. However, this one has a larger molecular weight, meaning it's going to have more dispersion forces within it. So it's going to have a higher boiling point. You're not expected to guess the boiling point, but you're going to be asked to rank it compared to other molecules. So now let's go through our next example. We're going to have a carbon with 4 methyls attached versus just pentane. Which one is going to have the higher boiling point here? So the answer is going to be pentane, and the reason is because when you have branching, as we do here, one thing to keep in mind, this has technically 1, 2, 3, 4, 5. So this is C5H12, and this also has 5 carbons. So they have the same molecular weight, but this one has more branching. Well, this one is just a straight chain alkane. When branching goes up, the surface area of the molecule goes down, meaning you have less London dispersion forces, which means you have less boiling point. So let's explain this concept real quick. If I have a molecule like pentane, the London dispersion forces are going to interact like this, but it's not really going to be favorable when you have a branched alkane, because you don't have as much surface area for interaction. So it's going to be harder to break up the bond between the atoms of this molecule than it is going to be of this one. So now let's go over CH3 CHO versus CH3 CH3. Which one's going to have a higher boiling point? Now notice that the molecular weight of these is almost identical, so that's not going to be the differentiating factor. The differentiating factor is going to be the OH at the end. Whenever you have an OH at the end, that's called an aldehyde, and the way it's drawn is this. You have an oxygen double bonded to a carbon. The CH3 is on the left side, and then you have hydrogen on the right. So this bond between the carbon and the oxygen, carbon has electronegativity of 2.5, and for oxygen it is going to be, I believe it's 3.5. Yeah. So since for oxygen it's higher, and it's higher than 0.5, this is going to have a partial negative charge, and this is going to have a partial positive charge. This value, the electronegativity, represents the strength by which the oxygen pulls on the electrons in this bond. So the electrons in this bond are going to be slightly closer to oxygen, which is going to make it slightly negative. And they're going to be slightly further away from the carbon, which is going to make it slightly positive. So that's going to mean that this molecule right here is going to be a polar molecule. But when you only have carbon and hydrogen, they have very close electronegativity values, so hydrocarbons that have nothing other than carbon and hydrogen, these are always going to be nonpolar. And polar molecules, polarity, as polarity goes up, the boiling point is always going to go up as well. The reason is because of the interaction that this is going to have with other molecules next to it. If you imagine another ethanol next to it, and the carbon has a partial positive, oxygen to the partial negative, there's going to be an electrostatic force of interaction between the carbon and the oxygen, because the negative or the opposite charges attract one another. And this interaction specifically is called London, it's not called London, it's called dipole interactions. So the dipole interactions are going to cause the boiling point to increase. And dipole interactions are stronger than London dispersion forces. So now let's compare CH3 CHO to CH3 CH2 OH. Which one of these is going to have the higher boiling point? So the answer is actually going to be, for this case, it's going to be the ethanol. Now let's be clear about the names here because they're very similar. The one on the left is called ethanol, and the one on the right is called ethanol. The left side this is an aldehyde, and this is an alcohol. Whenever you see OH like this written in the condensed formula, it's going to mean that you have an oxygen and a hydrogen attached to a hydrocarbon chain, and this is called a hydroxyl group or an alcohol. A lot of times you'll see it written like this, OH. It means the same thing as having the bond. It's just too cumbersome to draw the bond for some people. The aldehyde, we drew one last time, but I'll draw it again. That's what it looks like. Now the question is, these two look almost identical, right? Almost. They have almost the same molecular weight. Why is it that this one has a higher boiling point? It's because of a phenomenon called hydrogen bonding. Hydrogen bonding occurs when hydrogen bonds with fluorine, oxygen, or nitrogen. So the acronym is that hydrogen likes to have fun. F-O-N. The reason this occurs, once again, it is because of the electronegativity difference. Oxygen has 3.5, carbon has 2.1. And so the electrons are a little closer toward oxygen. The same thing is going to be true of carbon and oxygen, where oxygen is partially negative and carbon is partially positive. The difference here is that hydrogen doesn't have any electrons in its shell. It's just empty. Once these electrons that are in the bond go further away from it, hydrogen is a single proton. It only has one proton. So that one proton sitting in the center is not guarded by any electrons, and so the force that is created by it against things that are partially negative is going to be really high. So let's draw another ethanol. The interaction here, let's draw that better. This is called the hydrogen bond. That interaction is going to be a lot stronger than this interaction right here. So whenever you see two molecules that have generally the same molecular weight and they're both polar, but in one of them hydrogen bonds to fluorine, oxygen, or nitrogen, the one in which hydrogen bonds with these three is going to have hydrogen bonding, and therefore is going to have a higher boiling point. Now let's go over some halogens. If you have a hydrocarbon chain, and let's say in one of them you have fluorine, the other one you got chlorine, the other one you have bromine, and then you have iodine. Go ahead and rank the boiling point of these compared to one another. So I'm going to give you the values, and I'll explain why this is the case. Iodine, or really iodoethane, which this is called, is going to have the higher boiling point, and then it's going to go down from there toward fluorine. The reason this is because these molecules, all of them are nonpolar, and so the primary intermolecular force that is keeping them together is London dispersion forces. Now we talked about something where molecular weight, as it goes up, it also increases London dispersion forces. If you look at your periodic table, iodine has more protons and electrons than bromine, which has more protons and electrons than chlorine, which has more protons and electrons than fluorine. So as I move down, and this is the 7A row of the periodic table, these are the halogens. As you move down, the molecular weight of them is going to increase, which increases the London dispersion forces, which increases boiling point. So whenever you're asked in a test to, let's say, compare the boiling points of a hydrocarbon with the same number of carbons, one of them has a fluorine, the other one has a bromine, the one that has a bromine is going to be higher. And the order boiling point increases as you move down the periodic table for halogens. Alright. Let's go over another example where we're going to have an alcohol, which is propanol right here, and then we're going to have an amine. Which one of these has the higher boiling point? So notice here that both of these are polar molecules, and they all have hydrogen bonding, because the hydrogen here bonds with nitrogen and here it bonds with oxygen. And we said that hydrogen bonding occurs when hydrogen bonds with fluorine, oxygen, nitrogen. So it bonds with both of them in this case. But why does the ethanol have the higher boiling point? It's because when you look at the OH bond, oxygen's electronegativity is 3.5 and hydrogen's is 2.1. So the electronegativity difference is going to be equal to 1.4. When you look at the nitrogen hydrogen bond, nitrogen's electronegativity is 3.0 and carbon's is 2.1, meaning that the electronegativity difference is going to be 0.9. The higher the electronegativity difference, the more polar the bond is going to be, and the stronger the hydrogen bond is going to be. So therefore this one has a higher boiling point. So whenever you see an amine in an alcohol group that are placed in a similar carbon chain, so here we have 3 carbons, the alcohol is always going to have the higher boiling point because oxygen is more electronegative than nitrogen. Now let's go over some amines real quick. So compare these 3 molecules. Which one of these is going to have the higher boiling point? So notice here that in these 2 examples on the left, nitrogen does bond to hydrogen. But on this case, on here, you don't really see that. And maybe you think that it's bonding with the bonding with the hydrogen there, but it's really not. It's more like bonding with the carbon, which is bonding to the hydrogens. So here, we have no hydrogen bonding, but here, we do have hydrogen bonding. So we know automatically this is going to be number 3 when it comes to boiling point. 3 being the lowest in boiling point and 1 being the highest in boiling point. But now let's compare these 2. Which one of these is going to have the higher boiling point? We can see that they both have similar molecular weight. They have an amine group. They all have, looks like they all have 3 carbons. The differentiating factor is going to be how many hydrogen bonds they have. In this molecule, the nitrogen is bonded to 2 hydrogens. In this one, it's bonded to 1 hydrogen. And when nitrogen is bonded to more than 1 hydrogen, it's going to have a stronger hydrogen bond. And so it's going to have the higher boiling point. So this one is number 1, that's number 2, and then this is number 3. So to review here, when you have a first degree amine, it's going to be higher boiling point than a second degree amine, and it's higher boiling point than a third degree amine. And the way you tell that is the nitrogen connects to 1 carbon and 2 hydrogens. Here the nitrogen connects to 2 carbons and 1 hydrogen, and here the nitrogen connects to 3 carbons, no hydrogens. So that's it for this video. I hope it was helpful. Thank you for watching.